Today we're going to talk about energy and power. Back at the beginning of the course, we talked a little bit about what energy is, and we said at that time that energy is the ability to do work. And before we define work, let me just say it in a simpler way, and that is that an object with energy has the ability to do something. And the precise scientific definition is an object with energy has the ability to do work. And we'll talk about what that is. But again, if you think about an object that has energy, it can do something. So for example, a car that's already moving along the road at 50 miles per hour, it has the ability to keep moving. It has kinetic energy, the energy of motion. If I hold an object up and I let it go, it starts to fall. And so even before I let it fall, it must have some energy because it has the ability to fall. And that's called gravitational potential energy. So there are lots of different types of energy. And in this chapter, we're going to concentrate on kinetic energy, potential energy, and thermal energy. The important thing about energy is that energy is conserved. We call this conservation of energy. And what that means is energy cannot be created or destroyed. It can be transformed from one form into another or transferred from one object to another, but the total amount of energy never changes. You may remember in that first PowerPoint, I talked about my morning coffee and how energy to make that coffee started out as coal or some other fossil fuel and ultimately ended up as thermal energy or heat energy that allowed me to heat my coffee. So energy can be transferred from one object to another, and it can be transformed from one type to another. But the total amount of energy never changes. And we're going to use that concept of conservation of energy in this chapter. Let's talk about what is the definition of work. So work is defined as force times distance. And here I say that the force and the distance must be along the same direction. So for example, imagine I have a little toy car here, and I exert a force on that car, and I do that through a distance d. The work is just going to be equal to the force times the distance. Now, we know what's going to happen if I exert a force on a little toy car and then let go, I push it through a distance and then I let it go. We know that that car is now going to be moving. And so when you do work on an object, when you exert a force through a distance on an object, you're giving that object energy. In the case of that little toy car, when I give it a push over a certain distance, I'm giving that car kinetic energy. I also mentioned that when you do work on an object, you can be taking energy away from the object. As an example of that, imagine my little car is already moving in that direction and has some velocity. Well, I can take energy away from that car if I exert a force in the opposite direction to the direction that the car is moving. And if you think about when you're driving a real car, when you push on the accelerator pedal, your engine is doing work on the car. It's making the car move. When you step on the brake pedal, the brakes are doing work on the car, but in that case, they're taking energy away from the car. So when we do work, we can either give the object energy or take energy away. Let's look at what the units of work are. Since we know that work is equal to force times distance, that means that the units have to be the units of force, which are newtons, times the units of distance, which are meters. And because work is such an important concept, we give that a new unit, which is the joule. So the joule is the unit of energy in the metric system. All right, let's try out a problem. I pushed a toy car with a mass of 2 kilograms with a force of 5 newtons through a distance of 3 meters. How much work did I do on the car? And how much energy did the car gain? Okay, so I've got my little car. and it's got a mass of 2 kilograms. I exert a force of 5 newtons on the car, and I do that through a distance of 3 meters. Well, the first thing that you'll notice is to calculate how much work I do on the car, I don't need the mass of the car, I just need the force and the distance through which the force acted. In this case, I have 5 newtons times the distance, which is 3 meters, and therefore the work done is 15 joules. So that's the work that I do on the car. Now the next question is, how much energy did the car gain? Well, remember, when we do work on an object, we're either giving it energy or taking it away. In this case, we gave that car 15 joules of energy. So the answer is simply 15 joules. Now, one of the questions is, where did that energy go? What type of energy does the car now have? And the answer to that is kinetic energy. Kinetic energy is the energy of motion. So if something is moving, it has kinetic energy. The formula for calculating kinetic energy is 1/2 mv squared, where again m here is simply the mass of the object, and v is the velocity or speed of the object. Because kinetic energy is energy, the units are joules. And so you'll notice that we learned something about a joule. We said a joule is equal to a newton times a meter, but we can see from this formula it's also equal to kilograms times meters squared per second squared. Since velocity is meters per second, when we square it we get meters squared per second squared, and mass has units of kilograms. Alright, let's try out this problem. A car travels at 20 meters per second and has a mass of 1,000 kilograms. What's the kinetic energy of the car? So the kinetic energy of the car is simply 1/2 mv squared. So I take 1/2 times the mass, which is 1,000 kilograms, times the velocity, which is 20 meters per second, and I need to square that. And if you go ahead and do that on your calculator, you should get that the kinetic energy is 20,000 joules. Now that's for, a real size car. You'll notice that's a big number as opposed to my toy car problem where it was a little number. A joule is actually a fairly small unit of energy, and I'll give you another example to see that in a few minutes. So when we look at how much energy something like a real car has, it's a lot of joules, so a couple 100,000 joules. All right, let's combine a couple of the things that we've talked about now. We've talked about work, we've talked about conservation of energy, and we've talked about kinetic energy. So this problem says I push a toy car with a mass of 2 kilograms with a force of 5 newtons through a distance of 3 meters. If the car started from rest, how much kinetic energy does it end up with, and how fast is it going? So the first thing we have to do is figure out how much energy we gave to the car. Well, you'll notice the first part of this problem we already figured out previously. We figured out that the amount of work that we did on that car, which is just the force times the distance, or 5 newtons times 3 meters, and we came up with the fact that we gave the car 15 joules of energy. Well, where did that energy go? It went into the kinetic energy of the car. So the car, sorry, I spelled car with a K, thinking kinetic energy here. The car has 15 joules of kinetic energy after we're done pushing it. So if we know that the car has 15 joules of kinetic energy, we can figure out how fast it's going, because we know that kinetic energy is 1/2 mv squared. And now you see why I gave you the mass, because we're going to need the mass to find how fast it's going. So we have 15 joules is equal to 1/2 mv squared. So the first thing I'm going to do is multiply both sides by 2. So I get 30 is equal to mv squared. And now I'm going to divide both sides by the mass. And I'm going to just flip the direction here. I'm going to reverse the two terms. So v squared is equal to 30 divided by the mass. And the mass is 2 kilograms. So put that in. So I get v squared is equal to 15. And therefore v is equal to the square root of 15. And if you do that on your calculator, you'll find that it comes out to 3.87 meters per second. Just meters per second. And that would be how fast the car is going. Okay? So we use the concept of conservation of energy, that when I give energy to this car by doing work on it, that energy is now in the form of kinetic energy of the car. All right, the next type of energy we want to talk about is potential energy. And whenever you hear the term potential energy, think of stored energy. So for example, chemical potential energy is energy that's stored in the form of chemicals. So for example, when you buy a gallon of gasoline, you're buying chemical potential energy. That gasoline has the ability to do something once you release its energy in the engine of your car. The type of potential energy that we're going to be talking about in this section is gravitational potential energy. And let's look at how gravitational potential energy is defined. Gravitational potential energy is defined as m times g times h, where h is the height above the ground and g, the acceleration due to gravity, is 9.8 meters per second squared. So gravitational potential energy is the energy that something has due to its height. And remember, we said that if we hold something off the ground and we let it go, it's going to start falling. So it must already have energy. That's what we mean by gravitational potential energy, the stored energy that an object has just due to the fact that it's at some height h. So let's do a problem. What is the potential energy of a ball that's held 2 meters above the ground that has a mass of 1.5 kilograms? Well, to calculate that, I just use the formula. Potential energy is m times g times h. And so I have 1.5 kilograms. Multiply that by 9.8 meters per second squared. And multiply that by the height, which in this case is 2 meters. Now, when you calculate that with your calculator, what you're going to find is that you get 29.4. And the units there would be joules, because again, potential energy is a form of energy. All forms of energy have units of joules.